All right, let's move on with our circle geometry. Remember where we started. We started with this theorem, where there was a line that is drawn from the center of a circle perpendicular to a chord bisects the chord. We proved the theorem. The second one was a line drawn from the center of a circle to the midpoint of a chord is perpendicular to a chord, and we proved that it was indeed perpendicular. The next one was saying an angle subtended by the arc or a chord at the center of a circle is twice as the angle subtended by the same arc at the circumference. One must be at the center, the other one must be at the circumference. So this one is 2 times bigger than that one. That was the third theorem. The fourth one, this is the diameter. The angle formed by the diameter at the circumference is 90 degrees. Because this is 180, straight line, it is at the center, the one at the circumference must be half of that, which is 90. Angle at the center is 2 times bigger than the angle at the circumference. Number 5 that we've just done recently, this one, this arc subtends this angle at the circumference. The same arc subtends that angle at the circumference. This arc forms this angle at the circumference. The same arc forms that angle at the circumference. Therefore, these 2 angles are equal, simply because they are formed by the same arc. Now we move on to this next one. This line is called the tangent. This line is called the chord. The angle between the tangent and the chord, is equal to the angle in the alternate segment. That's the theorem that we're proving here. The angle between a tangent and a chord is equal to the angle in the alternate segment, in the other segment. How do you usually abbreviate this? We say this is the tan-chord theorem. When we want to abbreviate instead of, but it is important that we should know this in full, the angle between a tangent and a chord is equal to the angle in the alternate segment. So we refer to that as tan-chord theorem. We've got our diagram in this way. If this is our circle, this is our tangent, this then will be our chord. What is the chord doing? It divides the circle into 2 parts, this part and this part. Where is the angle, which is between the tangent and the chord? This is the position of the angle that is between the tangent and the chord. This is the position of this angle. Remember, the chord divides the circle into 2 parts. So the other angle that will be equal to this one must be on the other segment, not on this segment. It says the angle between a tangent and the chord is equal to the angle in the alternate segment. Alternate means other. So the angle between a tangent and a chord should be equal to the angle in the other segment, not the segment. So it should be equal to the angle in the alternate segment. So this chord must take us to the circumference. Right. So this angle is the same as this angle. This is what this theorem is saying. It's saying this angle is equal to that angle. Where is this angle? It is between the tangent and the chord. It can also come from this side. If the angle here, which is between a tangent and a chord, it must be equal to the angle in the circumference. So that angle there is equal to this angle here. So if we want to prove the theorem that says this angle is equal to that angle, let us prove that. If I've got here A, we've got B there, and we've got C here. Remember that theorems are step by step. The theorems get on top of each other at all times. Remember, in order for me to understand this one, I must understand that one. For me to understand this one, I must understand that one as well. If I want to understand this one, I can't do this one if I don't understand this one, because this is going to help me into proving the theorem. Let's do this thing. Number one, what is it that we want to prove? RTP. We want to prove that angle, let's call this C1. We want to prove that angle C1 is equals to angle A. This is what we want to prove. We want to prove that those two are the same. Let's not forget this is what we want to prove. Whatever we're doing, we want to come into this situation where we will say angle C1 is equal to A. In this diagram, we will say angle C1 is equal to A. Where is C1? It is between the tangent and the chord. The other one is on the other segment, alternate segment. Let's do our construction now. Remember, the construction is what is included in the diagram, which was not there, and it's always on dotted line. What is it that we're going to construct here? Let's construct a line that will come through the center. Through the center. What is it that we have joined? And also join this one. Right. If this is A, B, C, let's just call this one D. What is it that we have just constructed? We have joined DC and what? And DB. And DB. This is what we've constructed, and the construction is always on dotted lines. So that's what we've got, we've constructed so far, join. Right, join DC and DB. That's what we've joined. We've joined this line and that line. But the way that we join it, it should be such that this line DC passes through the center. If it doesn't pass through the center, we're going to experience problems. So make sure that it passes through the center of a circle. Why? Because I want to use the other theorem in order to help me. Remember, I want to prove that C1 is equals to angle A. That's what I want to prove. Let's do this thing. Now that I've got my construction, as soon as I do my construction, there's something that is telling me, this is the straight line, a diameter. This diameter forms that angle. If the diameter forms that angle, so what is the value of this angle here? It is 90 degrees. We're taking it from the fact that whenever we've got a diameter, if we take it into the circumference, the angle formed there will always be 90 degrees. So that's what we know. We know that this angle, it is 90 degrees, number one. We know that one. At the same time, all right, let's move on. If this angle is 90 degrees, what is this angle plus this angle? If I'm adding, remember the sum of interior angles of a triangle are supplementary. In other words, this angle plus this angle plus this angle is what? It is equals to 90 degrees. It is equal to 180 degrees. So this angle plus this angle plus this angle is 180 degrees. So only these two will give us 90 plus another 90 to get 180 degrees. Great. Let's move on. So we know this one is 90 degrees. As I do this, this is a radius and this is a tangent. Whenever a tangent meets a radius, I should always know that it will always be equals to 90 degrees. There's this theorem that I want us to look at here. There's this theorem that says whenever we've got a tangent and a radius, wherever they meet, they will always form 90 degrees. So that theorem is vitally important. So this is 90 degrees. Right. Look here. If I want to, in fact, let me just tell you what it is that we'll be doing. We want to show you that this angle will be equal to that angle. Once I show you that this angle is equal to this angle, this one will be equal to this. But let's move on nevertheless. Let's move on. We are saying if this one is 90, let's call this D. Okay. In triangle, in this triangle, in triangle DBC, in triangle DBC. That's the triangle I want to talk about. In triangle DBC, angle D plus angle B plus, let's call this C2. Let's call this one C2. In angle D plus angle B plus angle C2 is equals to 180 degrees. Are there any angles that I know that? Yes, there's one that I know. This angle, I know its value. It is 90 degrees. Where did you get that one from? From the fact that this was a diameter. Diameter forms 90 degrees. Angle subtended by the diameter is 90 degrees. And B is equals to 90 degrees. Subtended by the diameter. Diameter, what is this diameter? DC. Subtended by the diameter DC. Now, any angle that is subtended by the diameter, the circumference is 90 degrees. That's why I'm saying angle B is equal to 90 degrees. Right, what else do we have here? If I take this B this side, it will be minus 90. Remember that B is 90. If I take B this side, it will be 180 minus 90. Then I'll be left with D plus C equals, let's write that down. We've got angle D plus C2 equals to 90 degrees. Where did you get this 90 from? We took this B, which is 90. We took it on the other side. It becomes negative. 180 minus 90, it is 90. That's where it comes from. Now, I want us to make C2 the subject of the formula here. I want us to make C2 or even D. Let's make D the subject or C2 the subject. It doesn't matter. If I make D the subject, what will the value of D be? If I make D the subject, D will be equals to, look at it, D, angle D is equals to 90 degrees minus C2. This is what angle D is. It is equals to 90 degrees minus C2. So this angle D, if I want to make D the subject here, I've got to take C2 that side. So angle D will be equals to 90 minus C2. That's one fact that I wanted to get. So this becomes important because I'm going to use it. Right, let's take this a step further. Right, we now know our D is equals to 90 minus C2. What is going to be our C1? Look here. Whenever we've got a radius that is going to meet a tangent, it will always be 90 degrees. I want to bring my 90 again there. So I know that this is a radius from there to here, and it meets a tangent. So it simply means that, remember where we ended. We ended by saying D is equals to 90 degrees minus C2. Now I'm saying, if we've got a radius here, radius meets a tangent. So that is tan chord, tan radius. A radius is meeting a tangent. So we are saying here, angle C2 plus angle C1, it will give us 90 degrees. Why is this so? Because we've got tan radius. Tangent is meeting a radius. Tan radius. C1 plus C2 is equal to 90 degrees. All right. Let's look at C1, for example. What is C1 going to be? If we want to make C1 the subject, C1 will then be equals to 90 degrees minus C2. Right. C1 is equals to 90 degrees minus C2. Right? I said earlier on that this step is special. This one also is special. Let's look at the two statements. Why did I say, okay, C1 is equal to 90 minus C2. This is 90 minus C2, great. Let us look at the two statements. If I have D, what's the value of D? It is equal to 90 minus C2. What is C1? It is 90 minus C2. Okay, 90 minus C2 is the same as D, or 90 minus C2 is the same as C1. What can we say about these two? These two will be the same, because both of them are equal to 90 degrees minus C2. 90 minus C2 minus 90 minus C2. Therefore, we can safely say that C1, angle C1 is the same as D. Why are these two the same? Why am I saying C1 is the same as D? Because D is equal to 90 minus C2, as well as C1 is equal to 90 minus C2. Since both of them are equal to the same thing, therefore they are also equal. Why are they the same? Both equals to 90 degrees minus C2. Right. Now that we've established this fact that C1 is equals to angle D, let's look at that in our diagrams. Let's look at C1. This is where C1 is. We are saying this C1, we have just proved now that C1 is equal to angle D. Right. Let's look at this scenario now. Look at angle A. I'm saying to you, angle A is equals to angle C1. Angle A, look at angle A. If you look at this theorem, this is the arc, it subtends it there, the same arc subtends it there. So these two angles are the same. Look at this chord. This chord subtends this angle there, the same chord subtends that angle there. So this chord subtends equal angles at the circumference. Hence, this angle will be equal to this angle. If I've indicated this angle in two yellow lines, there's nothing stopping me from indicating this in two yellow lines. So I'm saying that this one is equal to, because it subtends this one, it also subtends this one. This chord CB subtends angle D at the circumference. The same chord or arc subtends angle A at the circumference. Therefore, these two angles are equal. I'm using the theorem of the same segment. Let's write this down. We are now saying angle D, look at this one. Angle A, because it is subtended by this arc, it is the same as angle D because it is subtended by the same arc. Let's write that down. We are saying angle A is the same as, this angle is the same as this angle, is the same as angle D. Why are these two the same? Why is angle A the same as angle D? They are subtended by the same arc, or the angles in the same segment, or subtended by the same arc or the same chord, or we just call them angles in the same segment. Let's look at what we have there. We are saying here, angle C1 is equal to D. We are also saying angle A is equal to D. What can we say about these two? Look at this one, it is D. Look at this one, it is D. What can we say about these two? They are the same. Therefore, we can conclude by saying angle A, or angle C1, is also equal to angle A. Why are these two angle A? Why are these two the same? Because they're both equal to D. What is it that we are required to prove? we're required to prove that angle C1 is equal to A, then we've just proved it. So this theorem says the angle between a tangent and a chord is equal to the angle in the alternate segment. To abbreviate it, we say tan chord theorem. Any angle that is between a tangent and a chord, it will always be equal to the angle on the alternate segment. There's nothing stopping us from coming from this side. This is the tangent, and this is the chord. You go to your chord, you go to the circumference. So this angle here, if we call this angle here y, this one will also be y, because this one is between a tangent and a chord. Go with your chord to the circumference. If I'm coming from this side, this is the tangent, this is the chord. I go to my chord, that is the circumference. So this angle is equal to this one. The angle between the tangent and the chord is equal to the angle in the alternate segment. Thank you.